There are four ways to induce air, in other words, to make air rise. If you take a look at these diagrams, here they are. Convectional lifting, that's the upper left-hand side. What that means is this: the ground gets hot, the air in contact with that ground gets hot, and hot air rises. Orographic lifting, which is the bottom diagram, that means that air is forced to rise up and over a mountain. This is the one we're going to focus on. Frontal lifting, which you can see in the upper right, that happens when warm and cold air masses meet and the warm air is forced to rise. And then cyclonic or convergent lifting, that happens in low pressure systems, as you can see on the bottom right hand corner. This is a great picture, not just because I took it, but because it is a great picture of orographic lifting. This is on the Big Island of Hawaii. And what you see happening is air rising up along the slopes of the major volcanoes there. And as it rises up, you can see that at one point there's no clouds, and then you can see there are clouds. And remember, we are going to determine with rising air whether we use the DAR or the WAR based on whether there's clouds. Because clouds mean 100% relative humidity, no clouds mean less than 100% relative humidity. So if you look at this picture, you can see where I drew the yellow line there. Everything above the yellow line, there's a cloud, the relative humidity has to be 100%. Everything below that yellow line, there's no cloud, even though the air is rising. And because of that, we can determine that the relative humidity must be less than 100%. This is the diagram we are going to use to do the math on. Okay, so we're going to look at orographic lifting, air that's rising up and over a mountain. Here's our mountain, and what's going to happen is this. The air, indicated by the blue arrow, is going to come along and it's going to hit the mountain. When it hits the mountain, it can't go through the mountain, so what does it do? It rises up and over the mountain. Now remember that wind generally blows from a particular direction most of the time. We call this the prevailing winds. In the case of California, the prevailing winds are out of the west. In other words, they're westerly winds. They come from the west, from the ocean on land. Because of that, as air hits a mountain and begins to rise up and over a mountain, we could generally distinguish with most mountains what's known as the windward and the leeward sides. The windward side is the side that faces the prevailing winds, and because of that, it tends to be the wet side. The leeward side is the side that's sheltered from the prevailing winds, and because of that, it tends to be the dry side. In other words, a lot of times on one side of a mountain, it tends to be wet and vegetated. On the other side of the mountain, it tends to be dry and desert. If you think about California, that's generally the way our mountains are. Because the leeward side is also the dry side, we also refer to the leeward side as a side that's in the rain shadow. In other words, there's not clouds, so no clouds, no rain. Now let's assume this. Let's assume as this air is rising up along the sides of the mountain, it's cooling, which it would be. And remember, as air temperature drops, relative humidity goes up. So as that air parcel is rising up along the sides of the mountain, it's cooling off. And when air temperature is going down, relative humidity is going up. Now let's assume this, that as that air is rising and it's cooling, right where I just drew that blue line, right here, that is the place where that rising parcel of air first cools to its dew point temperature. So air temperature, dew point temperature is the same number. The relative humidity is 100% and the air is saturated. At that point, a cloud is going to begin to form. There it is. That blue line, so in other words, the bottom of the clouds, the first place where the rising parcel of air reaches 100% relative humidity, saturation, and air temperature, dew point temperature are the same number, we call that elevation the condensation level. This is the elevation at which a rising parcel of air first cools to its dew point temperature. So air temperature, dew point temperature, same number. The relative humidity is 100%, the air is saturated, and the clouds begin to form. So you can see now by looking at this diagram why one side, the windward side, is the wet side, because there's clouds, and the other side, the leeward side, is the dry side. Okay. So this is a diagram of California. You can see the Sierra Nevada. And what happens where the Pacific Ocean is at, to the far western side of California? The air typically comes in off the Pacific Ocean. That's our prevailing westerly flow of air. It reaches the Sierra Nevada. It rises up along the Sierra Nevada. And as a result of that, the western slopes of the Sierra tend to be the wet side, the windward side. And then it descends and warms on the backside. And as it descends, that warming air is drying out. Remember, as air temperature goes up, relative humidity goes down. And because of that, typically on the backsides of our mountains, especially on the Sierra Nevada, what ends up happening is we have deserts. This is a satellite photo of the big island of Hawaii. Maybe you've been there. If you look, can you see which side is the windward side, the wet side, and which side is the leeward side, the dry side? In fact, if you ever go to the big island of Hawaii, what you're going to notice is this. One side, that's the Hilo side that I just circled, is one of the wettest places on Earth. Rains all the time because it sits all the time in the tropical easterly winds. The other side, the Kona side, is a desert because the air descends over the top of the mountains and then it comes down, and that's the Kona side. This is all desert over there. It's where a lot of the really big resorts are, actually, is on the Kona side. Okay, this is the math that we're going to do. So you can see that on the bottom left-hand corner over here, I have sea level and 0. This is where the air is going to begin to rise. Then over here, the condensation level is 6,000 feet. Then the top of the mountain is 11,000 feet. And you can see there's a cloud forming between 6,000 and 11,000 feet on the windward side. And then from 11,000 feet, the air is going to descend into this leeward side valley down to 3,000 feet. What we want to do before we do the math is we want to determine which rates we're going to use to calculate temperature change. So let's start with this. You can see now that the air temperature of this parcel of air is 72 degrees at sea level. And it's going to rise up to 6,000, the condensation level, then to 11,000, and then it's going to descend down to 3,000 feet. So between 0, sea level, and 6,000 feet on the windward side, is there a cloud forming right here? The answer is no. If the air is rising and there's no cloud, we are going to employ the DAR, 5.5 degrees Fahrenheit per 1,000 feet. Then look between 6,000 and 11,000 feet on the windward side. Is there a cloud forming there? Answer is yes. As a result of that, we're going to employ the WAR, because that means it's 100% relative humidity, as we can see with the cloud. 3.3 degrees Fahrenheit per 1,000 feet. Then the air is going to descend from 11,000 feet to 3,000 feet on the leeward side. Remember, every time the air descends, we use the DAR to calculate temperature change. Okay, the next video is the math.